Today we are going to solve this problem. All paths from source to target. From the example, it's a graph problem. So let's first read the description. Given a DAC, a directed acyclic graph, n node from 0 to n-1, find all possible paths from node 0 to the node n-1. Return in n order. We are given the input is a list of all nodes you can visit from node I. Okay, so we are given the corresponding node. For example, here the node 0 can go to node 1 and node 2. Node 1 only can go to 3. Node 2 can go node 3, and the node 3 cannot go anywhere, it's empty. And the final result will be 0, 1, 3, and 0, 2, 3. There are two possibilities we can traverse from 0 to the last one, 3. And let's see the function signature. We are going to return a list of lists, and given the 2D matrix, the graph. First, because we need to find the path from the start to target to the ending, we need to have the way to traverse the whole graph. And the way we are going to traverse this graph can using the DFS, depth first search, to accomplish that traverse for us. So we will given the parameter the start 0, and to see if we are ending the last node, which means it's the base case, we can put the current path into the final result. And if not, we will go back to the previous core stack, continue to traverse the next available node to build this path. Let's try to implement this idea. We have a result to collect all the valid data, and have the path to record all the paths we are currently on. Let's see the constraint. If the node can be 0, so if the input, the graph, is 0, we directly return the result. If not, we do the traverse called DFS, and the starting point will be 0, and we need to give the graph into this help function. After the traverse, we can get the final result. Define the signature about this one. It's start point, and given the whole graph here. So first, base case, if the start equal to the final, give the dimension of the graph. So if we go into the last one, here it's this one, we know we have a valid path, and we can return. If not, we are going to oh, by the way, the input is guaranteed have no have no cycle, so we don't need to use the visit. We don't need to check if the traverse on it already traversed or not. So it's we don't need that part in this problem. If we don't go to this base case, what we can do is the path we add the current one, and for each the neighbors in the graph this point, everything is possible. We do the DFS. Now the start point becomes this one, and we still give the graph here, and after this core return to this core stack, return to this level, and we need to reduce this part, remove the last of this current one, and it should work. Let's try to run it to verify. Oh no. So from this one we missed the last one, so somehow we needed to add the last one. So first coming to 0, if this one is last one, we can directly add this final result, so which means we needed to do this part first, then remove the last. So here it's missing the final one. If we go to the traverse to the final one, let's say 3, and in this case it's 3, it should add the path here. So let me try run to find the problem here using the first example here. Okay, so n is 4. Start first one is 0. It's not going here, and the path will have this one and 0 here. And for the neighborhood, oh, here I needed to let's use this one first. I call itself, and now the start is the neighbor have 2 neighbor 1 and 2 neighbor here. Graph the start, it's 1 and 2. So now the start will becoming 1. It's still not the end, so we will add this one here. And the one we have the neighbor 3. So in this case it's 3, DFS 3, here starts is 3, and now the start is becoming the last one. So here is the problem, which means we should not stop here. We needed to let this guy finished. Let's try this one. So we still don't go to the end here we still build this one, build 3 here, and 3's neighbor is empty, and we don't have the 3's, so in this case we will go to this part and it will directly remove, so the path here will remove 3. It will never go into this base case. So if I can run here, so if it should not be work, it's empty. Okay, so the problem is not here. The problem is how before we check the ending, so here we go to 3, we can go to 3, start becoming 3, I mean in this stage 3, and if we check it's the ending one, and maybe I believe I still need to add this start here and add the last one, then put into the final result. If not going this way, okay, it's still something wrong. I should not doing things here. So why it's not going to go through? Give me the final answer here. Okay, something wrong here. Let me check my previous to see why I'm wrong. So in this case, every time I add the current one in the first line, like here, whenever I go to this node, I will add this one, and then I do the validation, then the backtracking, then I remove the last one, do the traversing stuff. So if I add this one here, it will why it's still wrong? Start. Every time I come here and I do the check, I do the neighborhood traverse, then I remove the last one. To the current one. To the current one. Next one. Start. Why it's still wrong? We have add something. Do I need to don't return? Why I cannot return here? It's very weird. So if I go to the final one, I need to continue to this one, and I cannot return here. To me it's very weird. Let's see the official final result, how we do this one, and compare what's difference here. Let's define the backtracking and the path is linked list. Okay, first the path, add 0 here, and backtracking. What's the backtracking? It's current node, like here. The current node. Yes. Pass. Backtracking every time. We will add this guy, remove this one. So the difference here is to whenever the backtracking path is inside this for loop or outside this loop. That's the difference. If we go that way, the path, add the neighbor, and here the path, remove the path here, and we don't do the things here. Also, I need to modify the path, need to add the start point first. We have return here. So in this framework, and using the first example, can I see how long the video right now? Okay. So it's the backtracking framework. It's no longer the DFS. The interesting one, we are interested in the branch. I mean the edge, not the vertex itself. So if we're using this framework, the path will directly have the first one 0 here, and it's not passing, it's not the base case, and I will do the choice. Now the choice will be 1 or 2. Let's see, choice is 1, and the path will becoming 1 and 1. Here it's 1 and 2. We choose 1, and now the start will be 1. It's still not the last one, and we go from the 1. From 1 we can go where? We can go 3. So we will add the path 3 here. Okay, go down to the DFS function again. Check if this is the last one. It is. It will add this one into the final result. And we don't search again. We don't traverse again. We back to the previous core stack, which is here, and we remove the path. The path will be like here, and we try to do the next one in the one. The one only have this one, so we will go outside this loop and return to the previous stage, and the previous stage is 1 and 2, and we already done 1, and I will remove this one here, and we decide going to 2. So the start will be 2, and to append to the path here, path here, and okay, the 2, from the 2 I can go to the 3, and I add this 3 directly, add this 3 here, and this one will be touch the edge case, it will add to final result. It works. So if we do the backtracking part, it will look like here. The tricky part is you need to add the first element first, then inside this for loop do the backtracking. Let's run this again to verify everything is good. So to compare what I have done previous time, it's using like this way, and I cannot return here. I don't understand that part yet. So I will stick to the backtracking part and using this one right for now. And the time and the space complexity for this one, it will traverse the whole graph once, and in each steps you only have the constant operation, so the total time complexity will be O of Mn. The space one, we're using the path, the linked list to connect all the potentially paths, and the size will still be the total dimension of the input graph. So it's O of M multiple n. Let's verify the time space complexity. So here the space complexity will be possible. Oh, because we are to try each node, and we are interested in every single possibilities. Okay, so it will be to the exponential, and it's the same as the input size of the total node of the input graph. H extra space to store and return the result. Okay, if we don't count the final result space, we need the ON space to keep the current path. In the worst case, the current path will including all the nodes, so the space will be big O n, and the time complexity will be 2 exponential n times, and each step will take O n to build the path. Okay. Not very fluent in this problem. Maybe need to practice more in a few days. That's end for this problem. 797, all paths from source to target.